engineer for smart structures and materials. Chief
In Bangalore with Prof, we had a big conference, and they had tents outdoor, and of course they had an air conditioning inside there, so the air conditioner made a noise, and we needed loudspeakers, and energy was fighting against energy. So that doesn't make sense. So you allow me to take off my jacket? Because good. You are from which discipline?
I say this.
Sorry?
I say this automotive.
Automotive. So engineers. Are there also other disciplines here which are not engineers? You are all from the engineering discipline. Okay, welcome. So I know what language to talk. My background is also engineering. Who of you has heard something about non-destructive testing? Maybe except the ones who will come to Germany shortly. Do you know what non-destructive testing is? No? No idea?
Damaging the property of the test. It's the property of the material without damaging the material.
Without damaging the material, right. We find out the properties without damaging the material. That's what we're going to look at. Good. So I'll give you a little flavor because we don't have too much time, just 45 minutes. And I hope I'm able to convey things over to you. Sorry for the French, but it has nothing to do with Air France. It was just that when the airplane landed, there was a guy at the airport who took that photo. It's a very nasty situation, but it's incredible how the pilot made it in the end. But it's a situation which can happen, right? And of course, everybody of you sees this part is damaged here. That's obvious. You all made non-destructive testing here. 95% of non-destructive testing is done visual. On this one. What loads went through the whole structure of the wing here? What damaged that structure? Right. Now here on the right hand side you have some other accidents which happen sometimes. This is when suddenly the plane has to take off with a little too low speed, then it scratches on the back and it gets what is called a tail strike, and that needs to be repaired, and then hopefully the repair will stay. Maybe sometimes not stay. That's another situation. We all realize this guy is driving with a too heavy load. Everything went well, and he's going to deliver his load. But maybe after 3 months, suddenly something breaks, an axle breaks, and nobody knows why. So this is a little problematic situations we might be in. This is another situation where you're all familiar with the 747. The 747 has a big cargo door here. Into this cargo door, everything goes in. All heavy loads, whatever, elephants, cars, you can just imagine, all the things go in here. And this cabin is pressurized because we have animals and everything we can get into here. So what happens? Because the vehicles bump here on the lock may get deformed. The lock may get damaged. In that case, the door opened while the plane was in flight, when it was pressurized, and the plane was again back to land. Sorry, I have French in front of me. They landed in Paris, by the way. Good. At least it's still a miracle that the plane stays like this, right? But the other thing is, at critical locations, critical situations can happen. And doors, in that case, on the plane is something which is critical. That is just what happens when you fly too much in the hard condition. This is a plane landing, and what we see, this is not a French plane this time, and they lost the tail. The tail is lost here. Due to much repeated loading, we get damage on the structures, so we need to prevent that. And if you dismantle that structure, then you will see a lot of holes like this in the plane. Who of you has been flying on a plane? You of course have been flying. Many of you may have been flying, so you have all been flying on planes with cracks. You can be sure. Even because the planes, I also came back when they say the plane had certainly a crack. It was an old plane. So, but they can afford damages like this. Now those damages we can see with non-destructive testing. They are very obvious. But now, in reality, it looks like this because we don't see the damage. Right? Everything looks nice and flat and dynamic and So we need to look into this one, and this is the situation how people see cracks. So we have people who inspect the planes at fixed intervals, and they have to crawl in all sort of areas, and eventually they will find a crack like this one here. So we already see the crack is big. Right? That is quite big cracks. And there's cracks also happening a little hidden behind here. So with that mirror, you see the crack is coming out here. The crack obviously starting from here. So again, we have a decent big crack size. And there may be sealants also around. So we may not see the crack. So the crack is under that sealant somewhere. It grows. And we want, of course, to avoid that structures dismantling. And this is the tools which are used in more than 95% of the cases. So a very good training person with good eyes, with good understanding, and with tools like a torch, a magnifying glass, or magnifying glasses, and a special mirror. And this is how people crawl around in structures. Okay, we don't see the structure, but at least what you see here, if you design an airplane, and you design the structure of the airplane, then you see everything where it says CG, that means crack road. This means these are portions which are designed to allow to have cracks. So you see that huge portion up here, a huge portion down here, huge portion here, here, all those portions can be exposed to cracks. So there's a lot to expect, because not all the cracks are allowed to be very big. But this is how aeronautical structures are designed. So we need a lot of inspection to be done there. Now, to allow for that one, there is a specific design principle. Have you heard about fatigue? Metal fatigue? You bend something, you bend it many times, and then eventually it cracks. So do you know what sort of lines are characteristic to describe fatigue? Any idea? Have you heard something of a fatigue life curve? Or an SN curve? Well, what you do? Sorry? There is also endurance, correct? Endurance plays also a role. But what we determine a line which tells us how many cycles can we withstand a fatigue test under a certain load. So we take a component, we test the component, and then eventually it fractures at that line here. That's the number of cycles. Now we do the same test again, same material, same machining, same loading, everything is the same, and we fatigue it. Are we going to get the same fatigue life? No. Most likely not. So we get another fatigue life. And if we do another test, we'll get another fatigue life. Or we get another fatigue life. And another one, and that's just how it continues somewhere, then we finish. We say that's now enough. And what we get is the scatter time. That's all at the same loading. And if we got a high load, it will be up here. If we go down here, it's here. And then something happens that it goes basically horizontal. It's not quite sure if it's fully horizontal, but somehow it's horizontal. We call that one the endurance limit. So we say, yes, okay, so you've been at the fatigue lectures here. Yeah, so around 1 million cycle, depends a little on the material, something can be less, something can be more. It turns around here, and it goes into something where basically you can load it into very, very high number of cycles. So we get a line like this here, and what we see on that line, it scatters. And if we want to use that line to design something safe, such that it does not fracture, then we need to look at a portion which is this portion here. In this portion here, nothing is definitely going to fracture, right? If we are below that number of cycles. If we are inside that band here, it is going to fracture, but we don't know exactly when. It's like human life also, we're not getting all the same age, and we're not getting all the same disease at the same age. So there's a scatter, the same is also here. And then there's a range outside here where everything is scattered. So we're basically 3 areas. And if you want to design a structure now which is absolutely safe, then which curve are you going to take? Sorry? The
reverse.
You're going to take the 100%. You will take the 100%. What about the others?
Safely.
You take the other one. You take the 0. I would also take the 0. The 0 is safe. So you say to people, when you have achieved that number of cycles, scrap it, remove it. Now, if you remove all the components, well, you don't know how long it's going to last, and you have to be careful. There is a logarithmic scaling, which means the life from here to here, the life from here to here. So, if you can control exactly when your component is going to fracture, you may be able to extend the life by a factor of 2 or 3. Right? And that is for a big building, a big structure, something whatever. You take a turbine, a shaft, or something. That's a lot of money. But of course, there's also components which have to be safe life. Just you don't know what's happening. So, in principle, if you can control this area here, that you really know when is the crack coming, when is the crack going to be critical, then you're going to gain a lot of the potential of the material. So we can expand the life. Now you've seen aircraft before. You know roughly how long is the life of an aircraft? Operational life of an aircraft?
5 years.
What?
Maximum 5 years.
5 years. This is really the newest Indian airlines. No, it's a little more. It's a little more. But 30 years.
Maybe 10,000 hours.
Sorry?
10,000 hours.
What
10,000 hours.
10,000. Yes. Okay. You also take in hours. No, it's more hours than this one. It depends on what plane. It's 60,000 hours. They are now qualified even to 120,000 hours. But if you take it in years, we say usually about after 30 years, we scrap the plane. Have you flown in a plane that's 30 years old? You can't fully remember it. You know the Airbus A310? You know what that is. So that's a plane which is about 30 years old. That flew recently on one. There's not many airlines flying that one. So 30 years ago, it didn't know the airplane. And have you flown a plane which is 60 years old? That's as old as me. So, how do you find a plane which is 60 years? So, we're not interested to increase the life of the plane. But people in aerospace are taking advantage of this one. They are inspecting. Why are they doing this? Why are they so eager to look into structures and to inspect that they have damages? Because they don't want to extend the life. What else can they do? Sorry?
Send more planes.
Yes, okay, that's a good argument, but you're an engineer. You're not an economist. Whatever. Okay, that could be one argument, but that's not the argument. You can see on this diagram. On this diagram, they don't show rupees, euros, or dollars. How can you get out of this diagram with the other advantages? If you don't want to expand the life.
We know when to scrap it.
Sorry?
We know when to scrap it. When
Yes, okay,
limit
that's
of
the
the
economic reason. So you just scrap it and buy a new one. That's economic. Yes. But they don't do it from an economic point of view. They do it from an engineering point of view.
Safety.
Well, is it safe to fly with cracks?
No, it is not safe to fly. So when we know
Yes,
when the cracks
okay.
come, we can just
Yes,
dispose of
yes.
those.
But how do you see the advantage of this one out of this diagram?
So we can do reverse engineering.
We can do a
Reverse engineering.
reverse engineering. So how would you do a reverse engineering?
Testing and all.
You can test that one. Well, okay, well that's what you're doing. This is the result here. Now you have the result, and you want to take an advantage out of that result. The answer is very simple. You have two axes. What we've discussed at the moment is only in this direction. Right? Extend the life. If we're not interested in extending the life, we can increase the loads. So, let's increase the loads on the planes. How do we do this? How do we do it? Increase the load on the plane. Yeah, get more passengers on, get more cargo on. apply more maneuvers, or what else can you do? What else can you do?
Increasing the flying hour.
Sorry?
Raising the flying hour.
It's so noisy.
Increasing the flying hour.
Increasing the flight hours. Okay, but that would be again in this direction.
Range.
Loading. What does loading also mean?
Range.
You could, yeah, in the end you could get range, yes. But first of all, if you take off material from your structure, what's going to happen? We make things thinner. So, and we have the same load, what's going to happen? Sorry? It fractures, yes, it fractures at some time. That's exactly what we want to go into. But first of all, what increases? The stress, yes, of course. The stress goes up. So we take out material and the stress goes up and we go up here. So what does that mean? What's happening to the plane? Sorry? It fractures. It may fracture. We're going to prevent that it fractures. But first of all, what's the advantage we have if we take off material from the plane? It will be lighter. And what do we want to have in addition? Lightweight design, exactly. The best thing would be zero weight. So we can get the structure lighter weight if we can control the damage. So that's the whole secret of the lightweight design. And the aerospace people now even go further, and that's shown on the diagram down here. So that's what we discussed now here. That was our initial curve. This is micro damages, that's not interesting. This is where we control the damage. And then we can even go further, or we can say, let some things completely fracture. Let a frame fracture, let a string fracture, let a panel fracture. And other portions take over the loads, because it's not about to be critical, not about to collapse. But still, we can go further out here. And what we say here, it is then fail safe. So it's failed, but it is safe. And if we don't want to go in this direction, we go in this direction here. So we can gain again further lightweight potential. So this is the whole secret about lightweight design. And now, of course, you can only do that one if you can also inspect. So you need now inspection technologies to be able to operate in that lightweight design. And a similar thing would happen, because you can change the material, but you know that in automotive, if you change the composite material, it all makes it extremely more expensive. So this is what we can do here. So if you do a fatigue-like design, and so if you have done a little thing like this, you have your vehicle, you can take your car. People drive a certain way of the car, they may drive like whatever, Formula 1 or some sort of racing course. So you get an arbitrary sequence. For this one, you need to find out what is a cycle, what is a loading cycle. There's specific counting algorithms which you can use. And you count the cycles, and you put all the cycles in a matrix. And the matrix just shows you the distribution of cycles. So that's basically, I call that one the fingerprint of your driving. Or if you ride bikes is, by the way, one of the most excellent examples you can take. So each of us could get on a bike, we could monitor how you bike, and each of us would get a certain pattern. And now we want to know how long is the bike going to last, depending on the way you ride. And this one we can do by calculation, we can do by simulation, and we will get a fatigue life calculated. And the fatigue life is unfortunately, if you do a test, the test will be quite different. But at least what it tells you is there are areas where your damage accumulates more. And there's areas where your damage accumulates less. And it's because in those areas where damage accumulates more, where you have to look. And just imagine you have a big plane, because you cannot inspect the whole plane here, whatever, radiographically every 10,000 flight hours. So we will only go to the specific hotspots and look, has something happened? Because if nothing happened there, also nothing happened somewhere, should have happened somewhere else. Good, so that's sort of from a design point of view, the sequence. Good, now we allow for damage, and damage is of course cracks, as we're seeing. So we can describe a little, if we describe how a crack propagates over a number of cycles, then this is a sort of non-linear behavior. The longer the crack becomes at the same load, the quicker it propagates. You may also know that. If you pull on something and the crack is long, you have the same load and suddenly the crack propagates very quickly. Now, if this is the way how the crack propagates, and we can allow for cracks to exist in the structure, then we have three conditions. One condition is that we have of this calculated that even though we have a certain load sequence, we can afford for a certain crack length. If the crack is bigger, then of course there's a disaster going to happen. But if the crack is shorter, then we can still afford. So that's what we call the critical crack length adaptation. And now we need of course to know at which crack we start. Now if the structure has been used for a while, you cannot see a crack obviously, because those of you who know a little in material science know there's micro cracks. So there's a micro crack, but nobody can see how big the micro crack is, so we don't know how big the micro crack is. And you've also seen it's difficult to see specific crack length. At least we must have a crack length where we definitely know we have not seen a crack length which is bigger than that size. So if we would have samples here and all of you would have to see if you see the crack or not, we would have a certain statistical distribution. You might see cracks better than we might see, and you may even see better, and you may miss one completely. We would have a statistical distribution, but we would certainly have one crack length where we would say, this one we can guarantee everybody who is trained will see that crack. So that's what we're going to call the detectable crack. So if we inspect the UJ Prof structure, then we'll say, okay, we haven't seen any crack visually or whatever technique we have used, and we know there was definitely no crack which was bigger than this crack. So we assume in our crack propagation, this is the crack which we might have in our structure. And now we get the plane flying, and the question is how many flight cycles, how many flight hours is the plane allowed to fly? And from calculation we get a certain number of floating cycles. So that's what delta X says. And then we say, okay, so you need definitely to inspect before you have the number of delta N number of cycles. And usually, because we're good engineers, we say take half of it and look after half of it. So we get a procedure which looks like this one here. So that's the same like up here. That's the detectable crack length. This is the critical crack length. No, this is the critical crack length, sorry. And this is half of that life. And we inspect. We inspect at the locations which are critical. And we don't see a crack. So what does that mean? We don't see a crack. The crack is still not detectable. Why? So it means our assumptions we had before are still valid. So we take again the same. We say, okay, the cracks obviously not moved as much like here, so we still can start from here. Let's look again after a certain interval if something happens. And if again nothing happens, we continue, and we do that all the time until we find a crack. So that's what has happened here. And if we find a crack, then we have to repair. But the crack is still not critical, right? Because it's smaller than this crack. And this is what we call damage target design. So you realize inspection in that case plays a big role. Right, then there's a few additional things. That's the same thing we had here. Then there's of course which technique, and we're just going to look now a little into the different techniques which exist. And there are some techniques where you see the crack better and where you see it less. And we call that the probability of detection. So we assess even how good can cracks be seen. If I would give you a different crack length, then you would expect that each of us would have a different probability of detection. There would be cracks, you would see them 100%, and others you would not see them 100%. So this is an information you also need. Yeah. Sorry? MP, magnetic particle, I think. That's just taking some from publications that should be ultrasonic. Now don't ask me exactly who H, C, and P is. Maybe it's just the first names of the inspectors. Yeah. It should just show Good. So I think that's now clear. We can get life extension, or we can get a weight reduction. So this is life, at least in Germany or in Europe. We have a lot of highways, motorways, and we have that one in India in 40, 50 years, possibly the same. A lot of traffic, and the roads get whatever cracks here because there are more lorries, the bridges look whatever corroded, so you have people who have to inspect. And that's a huge effort to do the inspection. And that means that it somehow to be optimized. There's different ways how to do that. Then there's also another area which is energy generation in general. You can take coal, you can take oil. That's in the case of nuclear here. At least we want to expand the operational life, not in Germany, by the way. For example, in France, the life on nuclear power plants. And of course, you need to know the conditions if you want to do that one. So you need to go additionally with some inspection procedure. So that's absolutely crucial. Good. So that's a little thing which I've taken from my American colleagues. The National Science Foundation and some US colleagues got something nice assembled, and it's basically a little introduction into non-destructive testing. So that's basically what we're looking at, and that's the definition. Some of you already said it. Non-invasive. We are not going to make damage to a structure. So it's the use of non-invasive techniques to determine the integrity of the material, component, or structure, or to qualitatively measure a component. So we can even do a measurement for size, tolerances, thicknesses, and things like this. And that's just schematically. So we use waves. Waves is the absolutely essential things. Wave propagation. And whatever waves we use, we look how do those waves travel in those structures, and how they interact with damages, and how they interact with different conditions, etc. Good. Now you get a huge selection of methods of MBT. It takes quite a whack to get all the different methods here. Now some of them, like this one for example, you may know. If you got something fractured, the bones, etc., you will get X-ray. Or for other conditions, there's also ultrasonics. And there may be a few, you may also have some magnetic measurements or things like that. And there you see a variety of different, a huge selection of techniques. Not all are used at the same intensity, but we're going to look at a few ones which are essential. And what we're doing with those ones is, of course, to find flaws, evaluate flaws, but also to look, for example, at leakages. If we have a fracture in a pipe, and it leaks, we get it there. We also want to find out where the location is of the damage, and we can look at dimensions. We can look at the microstructure, the structure in general. We can characterize the materials, and we can set that one. We can estimate the mechanical and physical properties. We can also look at how are stresses and strains in those structures. We can measure those ones. And we can also just use it in processing. So we can sort materials, so we can differentiate materials, we can find, for example, partially chemical compositions of the materials. So you see there's a variety of things which can be done with that type of sensing. So where are they used? Well, in production development, to sort in chemical materials, to monitor and improve control of manufacturing processes, to verify proper processing, such as whatever heat treating, to verify proper assembly, and then to inspect in life what we just discussed here before regarding the aircraft. So you see, over the whole life cycle, you can even put in whatever in recycling. That's even missing. Right? If you dismantle things again, and people are doing this here, then even better. So these are the 6 most common techniques used. I've already mentioned. 95% is visual. Visual is what everybody basically does. You look, you think it's perfect or not. Then there's something called liquid penetrant. We'll just have a quick look at this one. Then there's magnetic techniques, ultrasonic techniques, eddy current techniques, X-ray techniques. So you see the electromagnetic waves are basically used in the whole range. And then there's also the acoustic ones, which are quite common. So visual inspection. Well, visual inspection is with eyes, but also of course with the help of eyes. So you see here, this gentleman is doing a little more. He has an endoscope, and he looks into some boreholes, whatever, some turbines or what they put in, right? And but you can also go a little further, and you may have seen that one, for example, that you have sort of cameras which you can send somewhere in pipes to inspect, and you have some articulating arms. That gets more and more popular. And you can even get that one built as a robot. So you have a robot which somehow goes through a pipe and inspects the pipe visually. Again. So there's a variety of techniques emerging there. Then we have liquid penetrant. And liquid penetrant is basically we have a liquid, a very, very fine dispersing liquid, and we wet the whole component with that liquid. And this liquid will eventually go into the cracks, if we have cracks on the surface of the component. And what we do now here, I don't exactly mix that some of the sequences here, but what we do then, after we took off the liquid, we're going to spray it with a powder, which basically is like a developer. And if the liquid is, for example, like in that case, green, or maybe even red, then the developer will somehow pour out the remaining red liquid from the cracks. And then we will see eventually on that white powdered component very small red lines, and we'll see, okay, this is where cracks are. And that's what it shows. We can even get that one amplified here with some ultraviolet lighting, and then you definitely see cracks and imperfections. So this is what the liquid penetrant inspection does. Then we can use magnetic particles, and with these ones we have again a crack, and we put the component under an electromagnetic field, and if we have cracks, then there's some discontinuities with the field lines here. And if we have again a dispersion liquid, magnetic particles, then they will concentrate exactly around the cracks, and we will see very nicely the crack specifically. So we can eliminate the whole thing with an ultraviolet light. These are a few cases which are very typical. You may have components which are overloaded, which might have got a crack or not, you're not quite sure. And this is how you get those inspected or gears here, and if you put them under the respective light, you can see quite nicely that there are cracks which you don't see otherwise. Right, then radiography is something very popular in medicine. This is basically this is the visible range, and you go to a high frequency electromagnetic wave here, so in the X-ray and gamma ray, depending on the source, we can either generate that artificially or we can generate it naturally. And what we do, we're going to send a radiographic signal through the component, and we will take an image, which we can take digitally or we can take on a film, and we will see on the image a sort of resolution depending on flows being inside there. We can do this one at different levels. We can do that one from different directions, and we can get a full 3D image of what we're looking into. And we can get that very, very high resolution. But of course, the effort is not a small one. These are some radiographic images. You see specifically very nice, tiny, small components. It's able to show imperfection inside there, but also here in those pressure vessels, there's some artificial things which have been put here into the component, which can be seen here. Then there's a technique which is very widely used, which is eddy current testing. So what we have here is we have a coil, and that coil we apply an alternating current, and with the alternating current that generates a magnetic field. And if this magnetic field interacts with something which is conductive, then we get a conduction, and the change of the induction is a sign of the condition. It either tells us what material is this, or how is the condition of that material. And out of this interaction, we operate. Now, we're not going into the details of that one, but there's a variety of applications. It's specifically popular in tiny components, whatever we find in the holes. You see, he has a little coil here, and he inspects here whatever the surface condition, obviously on that cylinder or whatever automotive supply component that is. Then we have ultrasonic, sort of a technique which is after visual possibly the one most used. And what we have here, we send in an acoustic impulse, and the acoustic wave goes through and is reflected and interferences and goes back again. And if we have a flow, then it's reflected a little earlier, and we basically take a time signal here. So this is the initial pulse. This is what we call the back surface echo coming from here. So we can do, for example, the thickness measurement of it. And if we have a flow in between, we'll get signals in between. So we'll see if something is not perfect inside that material. Ultrasonic imaging is totally popular. One of them is just to put components into an immersion tank and scan the whole components and get full 3D images of those structures. That's a little what schematically comes out. There's a lot of simulation work those days, specifically here. The French colleagues make, I don't know if you know, but your big organization, CEA, has a software called CIVA, which is a little the standard of simulation of NDT. So that's also one of the things. Right, and then you can get images of all sort of resolution. This is showing the coin from the front, and this is showing the coin from the rear side, but the image going through the coin from the front. So you still look at the front, but you get the reflected signal from the rear side. Good. Now, a little common applications just for the end. It's raw products, following processing, and in-service damage. And here you have a few cases. For example, manufactured steel components, forgings, castings, extrusions. So it is a possibility either in process, what we call inline, or offline to inspect the components regarding their various conditions. Then you can apply things, machining, treating it, whatever, welding, grinding, heat treatment, plating, all those things. It is used, again, it can be used even in process, in line, depending on how the conditions are. And then it's in service damages which have occurred. Have you overloaded your components? And because here it's clear it's fractured, it's also clear it has leaked. But then you can also, where the crack gradually starts and where the corrosion gradually starts, and for those ones you need to get that one checked. Now, as I said before, energy is a huge sector. Power plants, heat exchangers, this is the case which you see here. So in all the heat exchanger pipes, this gentleman is sending in that case, an eddy current probe, and he looks how is the response, and if the response is good, then the pipe is good. Otherwise, if there's damage on the heat exchanger, then a repair is required. That is something not really for Tamil Nadu, because you don't go for skiing here. But we have, because elevators also here, so there you also have ropes, at least the inspection of ropes, and we don't want those ones to fracture, so you can use, for example, magnetic methods here, and that to inspect ropes all the time when it is required. Then another big field is storage tank inspection. We don't want to have a leakage, and of course, depending on what you have in your storage tank, you may have corrosive influences. And for this one, specifically since the tank is quite big, you can, for example, have little crawlers on the outside which inspect those ones, sort of little robotic systems, which maybe if the tank is even metal, you can have magnetic wheels and being built that way. Or you may have inside, again, a visual system, like, for example, an articulating camera here, and the camera looks, for example, in the inside, if it is whatever water storage or whatever is stored there. Then aircraft inspection, I think I've mentioned more than enough, so there's a variety of things which happen, so we use all the different techniques there. And jet engines is a huge sector of this because it's very highly loaded, and all those notches here are quite critical. You see they use very much liquid penetrant, by the way, but maybe that could be also, but it's obviously the cheapest and still the most reliable technique they can use here. And if that is overseen, the damage, then unfortunately accidents like this happen. This is a disc which fractured, unfortunately during landing, when the engine was at a very high RPM, and a crash happened. That is a few years back. And then pressure vessels is also a large area wherever you store gas or similar things here, and that in that case is done radiographically with the film technique. And railways is also a big sector. The rails itself, like you see here, so there's trains inspecting the rails on a fairly continuous basis, so you avoid, hopefully, rails to fracture and the train to derail. But there's also another big sector, by the way, to inspect axles of trains. Axles is also an issue, specifically on the high-speed trains. We had, unfortunately in Germany, a few cases which need to be solved. Then there's a huge thing currently coming up in terms of bridges. You see the US, these are statistics here in the US. The US has nearly 600,000 bridges. India has also a large number of bridges. And railway in India is also, I think, quite, well, you have more than 100 years railway here. So your bridges maybe also, you may have bridges which are more than 100 years old. And those things need somehow to be maintained, to be inspected. So, and you realize this is not a very easy task. Then pipelines is a big area. And that's basically using robotic systems, which is called pigs or molds, which are systems like this one here, depending on the size of the pipeline. So it's basically, this inspection system is pushed through the pipeline over hundreds of kilometers and takes data continuously to gather information about corrosion, thickness change, dents, or there even geotechnical movements. Right? And so this is a very, very high sophisticated system going through those pipelines. And then, of course, if that pig has which called is pig, I forgot what pig stands. Sorry, gauge inspection. Pipeline inspection gauge. That's what it stands for. Yeah. And then once you find the location where something has happened, then you can go a little more in detail and inspect a little more in detail. There, like for example, like those people are doing that radiographic inspection, obviously somewhere in a place where it's very cold. And then there's special measurements in the end, where the cultural heritage is, for example, also a very interesting area to inspect. Right. So, and there's more things coming. That's just for a little here for the end. A technique called multi-sensing or sampling phased array or phased array in general. So what we have here is that we have different piezoelectric transducers where one is sending out the signal, and you see it's reflected by the flows, and all the transducers get a response signal. And we do all the combinations of those ones, and we fill a matrix here with all the time domain signals. So we get a huge database with a lot of data, but that's not too much of a problem today because we have enough computer capacity. And with this one now, we can play around with those data. We can sort of merge them, we can superimpose and what we call phase shift the data until we get a maximum resolution. And this is basically what happens. If this is again your phased array transducers, you have many little transducers in one block, that's what we call phased array. And we get one to send. And then if this is the component and these are the different flows, then these are the responses which we get here again. We only know there's a response signal coming, and we know in that hemisphere something must have happened. So we do that one with the next combination, and then we see, okay, there's something concentrating here, something concentrating here. If we do all the combinations through, you realize we continuously improve the resolution, because it points continuously that really on that imperfection. And this is, of course, which is sort of I would say the latest standard in acoustic testing those days, using phased array technique and getting fairly high resolution. A fairly high resolution not just in 2D, but even in 3D. And this is, by the way, also the image which you can only communicate to people. Right? The data before, it's very, very difficult to communicate. Good. I think that's what I have to say. If you have any questions, we still have 2 minutes, and we're just at time. Any questions? Useful? Not useful? Do you want to study more? I haven't made an advert, but come to see us. We also, by the way, have a master course in NDT only for 2 years. And that's even what we're discussing here with the Baltic University. Maybe in the future, the one or the other may be able to join us on this one, if that is something which you feel is interesting for engineering. Any questions? Not at the moment? Good. Done? Thank you for listening. I just hope it was somehow a little inspiring, and we may see you again. Oh, yes. Quite known here, and Dr. Peter Starker, who is the person who's mainly doing those things with that 5-over-T testing and separation testing, very important. A DSC with. Good. Thank you very much for listening, and I hope now for any sort of questions you have, and any sort of things you want to discuss, or problems you have, or maybe you have even things which are very individual, and we'll talk those ones separately. We don't want to talk those ones